Right, so I think we are live now. Yes, yes, we are. So folks, so again, the goal of this lesson and the next lesson is to sort of give you a clear path through this, sea of the facts that are thrown at you in these sections, the sections on graphing, and hopefully even though I'm not going to ask you to graph a function based on the study of its derivatives and things like that, there's going to be some questions, some more pointed questions, which I'm going to make a selection of and I'm going to post in Canvas. And that selection of questions, folks, will be used to generate exam problems as well. So not necessarily exactly those, but along the same in the same circle of ideas. So I want to make sure that everybody understands what's asked from you when it comes to graphing, to the graphing section. And I'm going to share with you the whiteboard, and as usual, I am going to write here, folks. So I'm not sure if my camera shows well because I can't see that, but the whiteboard should show properly. So what I'm doing here, folks, in this lesson, I want to do a quick review. So first of all, limits at infinity, because these are important. We did those yesterday. I just want to remind everybody what they are and why they are important. Again, yesterday we mentioned that these limits at infinity are sort of some anchors for the graph of a function when you look at how far it goes to infinity. So sometimes there is no limit at infinity, and then you don't have those anchors. So the graph may be very strangely go something like this. Let's say this is the x-axis. All right, so we don't need that for the limit, although we can say a limit there too. So what we need to sort of try to anchor these things when they get closer and closer here, down here. So can you anchor? Can you say that towards infinity, the graph actually sort of lands on this line here? And also over here, I mean, can you say maybe it lands on a different line when it goes to negative infinity? We didn't do any limits, by the way, at negative infinity, but they work the exact same way as the one to at infinity. I'm going to do an example today. So can you figure out these sort of things? So these are the horizontal asymptotes, or the limits at infinity. So from a point of view of graphing something, limit at infinity and horizontal asymptote is essentially the same thing, except that the limit is a number, or so it's a number in this case. If you want to find those horizontal asymptotes, you got to be a number. The horizontal asymptote is the line y equals that number. That's your limit. So that's what I need to address today. I need to give you yet another example. I point out that these are so important for graphing purposes. When you want to graph a function, if you can take care of most of the stuff, say in this direction and in this direction, you sort of know the shape. All you have to do is focus on this smaller area. So at least you have a hope to actually say something concrete in more detail, get some more detail about the function here. So with these limits at infinity, you have to address basically what happens in these parts that are far away to the left, far away to the right. And I'm going to do an example today, and that example is a limit at negative infinity, and that's going to be this. What is the function? Sorry. Okay. So I selected here. So there we go. So it's number 12. I had it marked, but I couldn't see it. So number 12 from 3.4. All right, I'm going to copy that. And it's a limit, again, a limit as x goes to negative infinity of the following thing. So it's going to be 4x cubed plus 6x squared minus 2 divided by 2x cubed minus 4x plus 5. Now, this is a bit of a warm-up exercise. So let's remember what we did yesterday. So yesterday we said that when you calculate the limit at infinity or negative infinity or so, what you could do in this case, you could use a table of values. So you could represent, you could take this function f of x equals this thing. You could go to Desmos, and that's an option, folks. Go to Desmos and plug in numbers x that are 10, 100, 1,000, yada, 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 so very large numbers, and figure out what the values of this function are. And you could figure out what the limit is that way. And I'm going to do it that way so that, people have, again, that dual situation in mind. And I'm going to share that with you. And I'll share that with you. So let's go ahead here. So, okay, sorry, wrong page. You don't care about this, I guess. What is that thing? Oops. Sorry about that, folks. I need to move this out of the way. So let's, okay. So now that, okay, Desmos. All right. So we go to Desmos and we're going to take the exact same function and do what we said. So we're going to say, we're going to call that function a formula. We're going to call it f of x is 4x cubed plus 6x squared minus 2, 4x cubed, oops, sorry about it, plus 6x squared minus 2 divided by, and at the bottom we have 2x cubed minus 4x plus 5. Oops. 2x cubed minus 4x plus 5. There we go. So this is, it's an ugly function. So anyway, so the limit as x goes to negative infinity will be found by using the following table. So in the table, as I said, we're going to put the, oops. No, I don't want to do that. No, I want to do t here. So I somehow popped up in the previous box. So I'm going to put the table here. So there we go. I'm going to put t here. And I'm going to put f of t in this column. And I'm going to do 10, and then 100, and then 1,000, and then 10,000, and so on and so forth. And if I do this here, I see that the values of f go from 2.33, 2.03, 2.003, 2.003, and I think it's pretty clear that these values are getting closer and closer to 2. So I'm gonna stop sharing this screen and I'm gonna share the other screen with you, the whiteboard, and I'm gonna say, you know what? We guessed with a table that the limit is 2. Now, I want to show you how to do this algebraically. So let's review the algebraic method because that's important. So it's not always easy to do that. Well, actually, I think you can do most of the time. You can do Desmos if you want, and on the test too. But I wanna see your work. So the algebraic method goes by simply the algebraic method, folks. Oops. Algebraic method goes by simply wiping out so keeping the higher power. So we said that when it comes to limits at infinity, the big fish eats the small fish. So the higher powers, they eat up the remaining part of the expression. So they eat up that and that correspondingly top and bottom. And we end up with 4x cubed divided by 2x cubed. And that's 4/2 or 2. So that's what we end up with, my friends. And that is the limit. So it simplifies down to 2 and we are done. So it's that simple to do it algebraically. Now, some limits, so it doesn't really matter that it's negative infinity or infinity here. It turns out that the limit is 2 in both cases. If we look back at Desmos, so okay, so what is that now? Okay, so let's see. Okay, so let's look back at Desmos. New share. You will see that indeed the limit at negative infinity goes very, very close to 2. So let me just, there we go. So you see that, there we go. It's very, very close to 2. Oh, you know what? I calculated the wrong limit. I calculated the limit at infinity, not at negative infinity. So if I want negative infinity, what I would do, folks, I would do negative 10. Oh, there we go. So negative 100. Negative 1,000 and negative 10,000. And there we go. So yeah, this is also going to 2. So on both sides, luckily, it goes to 2 in both directions. So we don't really have to worry. But some cases, there would be different limits at negative infinity and at positive infinity. So that being said, I'm going to give you such an example of a function that has different limits at positive and negative infinity. And that will be the function used in number 20. And let's look at number 20 together because this is an important example. And this is going to be the last one that I'm going to do from this lesson. I think it's very illustrative for what we do here. So let's move this up a little bit here. And let's go ahead here and let's calculate the limit in number 20 of section 3.4. The limit as x goes to infinity, x plus 3x squared divided by 4x minus 1. All right, so we have that limit, and we're also going to calculate this other limit, the limit as x goes to negative infinity of the same thing, x plus 3x squared divided by 4x minus 1. And you will see that in this case, we get different limits. So here's what happens, folks. Again, the idea is to take this expression, x plus 3x squared and 4x minus 1, circle out the highest powers, which you got to be careful here are this one at the top and this one at the bottom. So they're not in their traditional places. And if you use the rule of big fish eats the small fish, you get 3x squared by 4x, and that is going to be, when you divide out, it's going to be 3/4 x. And with that being said, is the value of the limit at infinity will be, you have to substitute this time around because you have an x there, so there shouldn't be an x in the limit. So you have to substitute. At infinity, that means x is infinity. So 3/4 times infinity is going to be the number infinity. So any constant times infinity is infinity. However, different things happen when the limit is going to negative infinity. So you have 3/4 from this expression, the same expression, right? But this time around is going to be times negative infinity, and it turns out that the limit here is negative infinity. So here's what happens, my friends. When you go to the right, your function is going all the way up. When you go to the left, your function is going to go all the way down to the left. And we will see that that's the case with this function going back to Desmos. So I'm going to copy, number 20. All right, so I'm going to have a different function here, and my function is, I'm going to increase this thing, and you know what? I'm just going to, I could have kept the table too. I'm just going to copy x plus 3x squared all right, divided by 4x minus 1. All right, so here's what happens. So this is a function that has a bit of a problem, as you can see. So I should probably say x different from, oh, okay, so there we go. There we go. It was, sorry, folks, it was zoomed out too much. But here's the idea. As x goes to infinity, you go up here towards infinity that way, and you go down here towards negative infinity when you go down. So no surprise, we just figured out that the limits at infinity and negative infinity will be plus and minus infinity. If you want to do a table, you can check that with a table. So you can easily check that with a table, really. So you just put the numbers t here and f of t over here. And this is the function, so we're just going to give values 10, 100, 1,000, 10,000, and so on. So you can see that the limit as x goes to infinity, it does really increase. So let's say 100 or 1 million or something like that. So there we go. So it's becoming larger and larger, this number, 10 million over here. But what happens when the same numbers, let's do another table here, and let's say, what happens when this number, let's call the new variable s. I'm going to call this f of s. And the numbers over here are negative 10, oops, and negative 100, then negative 1,000, and so on. And you can put as large as close to negative infinity as you want of a number. So you can put negative 1 million. I'm not counting properly, but well, there we go. So the numbers are very, very, very negative. So in the direction of negative infinity. So you can see that those limits that we just talked about are confirmed here numerically. So whichever one of these you choose, folks, is all fine to me. Just make sure that you have the correct math there when you do that on the test. So this is the discussion with these limits at plus and minus infinity. And again, this is the last time when we talk about limits. We won't talk about limits anymore in this class. The next time around, when you talk about limits, would be in calculus 2. If any of you takes calculus 2, maybe talk to me at towards the end of this class for a few pointers. You need to review a number of things before you move on there, because it's it's a different type of subject, really, in many ways. And you use a lot of these things, but not quite everything. Then, and you got to be more focused on some other issues than we are here. All right. So that being said, I am going to stop sharing this, and I'm going to go back to the to the whiteboard, and I'm going to be done. This is my entire discussion. This is where my discussion about limits ends. And I'm going to move on to the next page. And we're going to do a little bit of curve sketching yet again. Yesterday's lesson ended up with some discussion about graphs and the shapes of graphs and things like that. And we're coming back today, and we say, oh, let's do curve sketching yet again. So what is the difference? So I'm going to start lesson 3.5. Curve sketching is a very very nice thing to do by hand. But as I told you, it's a bit of an old-fashioned topic right now, because with the advance in the computer power and all that, all you have to do is to go to Desmos, and there we go. Desmos solves all your problems of curve sketching sometimes. Not all of them, but you know, it's nice to know. It's nice to know, folks. Although in practice, as I said, you probably will never do this by hand, but it's nice to know how to sketch the graph of a function by you know, analyzing its first and second derivatives and so on. So what I'm going to do here, I'm going to do a summary of curve sketching, and then I'll discuss what is new in this lesson. Or maybe let's discuss what is new here. So what is new? Well, there isn't much new stuff. So same stories, same criterion, same criteria, because there's a couple of them, let's say criteria here. And they are that f is increasing. And I kept pounding with this thing. Oh, well, if f prime is positive and f is decreasing, if and only if f prime is negative. F prime, I'm sorry. Yes, this is correct. I didn't want to. I didn't want to mention decrease. Well, we said decreasing here. So I wanted to mention f is concave up. If and only if f prime prime is positive and concave down. If and only if f prime prime is negative. So I want to you to keep in mind that these are the criteria that we did in lesson 3.3. So it's nothing new here, really, folks. So this is from 3.3. So you're saying, okay, so we figure out where f is increasing, we figure out where it's decreasing, we figure the maximum and minimum points and things like that. What else do we need for a function? Well, so the only thing that we really add new here is the limits at infinity, which we didn't use, and a little bit of a discussion about vertical asymptotes when the graph breaks down. So the only thing that's really new here would be you know, horizontal and vertical asymptotes. And of these two, the horizontal asymptotes is the limit as x goes to plus minus infinity. So it's actually known. So the only new thing will be a little bit of a discussion about these vertical asymptotes, which you actually did in pre-calculus and after the college algebra and so on. So there isn't really anything new here. So it's just a review of vertical asymptotes. This is the only new thing here, a review of vertical asymptotes from your college algebra days. So here's the deal with those vertical asymptotes. Sometimes the graph of a function turns out to be something like this: x squared plus 1 divided by x minus 3. And you know that the function is undefined at 3, so it's got to be undefined because if you put 3 in here, you get you know, 10 divided by 0. That doesn't make sense. That's nonsense. So you want to make sure that x is not equal to 3. But the question is, what happens around 3 to the left and to the right? Yeah, so it doesn't exist at 3, but close to 3, what happens? And it turns out that this one function is actually has a vertical asymptote. In other words, if you draw the graph, so let's say this is 3 over here, and I'm going to draw the asymptote with red. So this straight line would be going down with red. So if you draw a graph of this function, it's going to look something like this, folks. I'm going to draw a graph of, let's do it with, let's do it with blue. So the graph of this function will be close like that over here, and maybe something like that over here. So I don't know exactly what the graph looks like, but I know for sure that it's going to be really close to this thing. How do I know which way, going down or up? Well, that would be by calculating the limits from the left and from the right, right? Because limit from the right, I claim that would be positive infinity. Why would that be? Well, because if you calculate again, so it's a bit of a limit question here. If you calculate the limit as x goes to 3 plus, so from the right side, right? So values of x larger than 3, then what we have here is, numbers very close to 10. And over here at the bottom, numbers, it's very close to 3, so it's positive, but very, very tiny. So when you divide by a very tiny number, that makes the quotient blow up to infinity. So it's this is a situation of what we call 10 divided by 0 plus. So in the book they basically make you memorize. Well, this is the infinity, right? But I think if you just use logic, you can figure this out. Now there is an even easier way without using limits by simply, folks, using a calculator and giving a value to x very, very close to 3. So you just use a value. And if that value is infinity, is very close to, well, very large number, you can't suspect that will be close to positive infinity. A few other things could happen that would scramble this entire process. So this is not a permanent solution. This is just a temporary solution. But, if you have a gut feeling that, the limit here must be infinity or negative infinity, and you don't know which one to choose, you might want to choose a value, and that's going to tell you the sign at least. If there are other issues here and the limit, it could be that the limit doesn't exist, well, then the problem is significantly more complex. But, this is it. This is the discussion about these vertical asymptotes. How do you find the vertical asymptotes, the red line? So vertical asymptotes can be found where the denominator is 0. So that is x equals 3 in my case. Denominator 0. All right, so that's essentially where you find these vertical asymptotes. There could be other trickier things, but this is pretty much, I think pretty much as we will ever see, you will ever see in practice, if you will ever see these kind of things. So that is the issue that needs to be discussed there. The next thing is putting all these things together. The discussion that we carried out up to this point, the discussion with limits at infinity, and the discussion with concave up and down and increasing and decreasing, putting these together and drawing the graph of a function. And I am going to do one example like that. So I'm going to do just one example, folks. It's not going to be many. Again, I don't want to spend too much time on this section because it's one of those things that you could take for the time and time again to do these things, but you got to keep things relatively simple at some point. So let's do number 9. All right, folks. So I'm going to do number 9 here from section 3.6. And number 9 is about the following function, y equals x divided by x minus 1. So this is a function. This is a function that does have all sorts of all the elements that we needed in this particular problem. So we want to graph it, and we're going to draw a graph by hand. And let's go ahead and let's figure out the elements that we discussed. So we discussed that we need to take a look at where the function is defined to begin with, to rule out those situations with vertical asymptotes, and also rule out, to kind of take care of the behavior towards infinity and negative infinity. So to do so, we're going to look at vertical asymptotes. All right, and it does have one, and that is where x minus 1 is equal to 0 or x equals 1. Now, remember, folks, from college algebra or from pre-calculus, so a vertical line would have this kind of equation, x equals something, because it's, all the x's, all the numbers with the same x piled up on top of each other. So this is where the vertical asymptote is. There is only one, this one here, x equals 1. Number 2, horizontal asymptotes. By the way, given the vertical asymptote, we're going to say, I should have said earlier that the domain of this function, you want to exclude all the x's other than 1. You cannot substitute 1 in here. So I'm going to say, I'm going to write it interval notation, negative infinity to 1, along with the interval 1 to infinity, where we skip 1 very well. So, horizontal asymptotes are the following thing. You calculate the limits as x goes to infinity of x divided by x minus 1. And you could see easily here, there's no other thing than x at the top, but over here at the bottom we have x and it's up 1. So this is really going to be x over x or 1. And this, you could see that it doesn't really matter if I have plus or minus infinity, because anyway, that simplifies out, it turns out to be 1. So I'm going to say the line y equals 1 is a horizontal asymptote. What that means, folks, it means that the graph towards infinity and towards negative infinity, it flattens out at the level of y equals 1. Finally, we can now discuss about what happens in between these things, in between these asymptotes and such. And we're going to see where the function is increasing, decreasing, concave up, and concave down. In order to do so, we are going to look at the derivatives. So the derivatives are the following, and that's going to be here. So what do we have? X over x minus 1, right? So we have x prime. Why do I have to calculate the derivative? Again, remember that, so over here, folks, the function is increasing is decided by the sign of a derivative. So that's why we have to calculate. Yeah. All right. So y prime is x prime times x minus 1 minus x times x minus 1 primed, all divided by x minus 1 squared. And of course, this has got to be different from 1x here, but it's not going to be a big deal. You will see in a second, because, x prime is 1. So we got x minus 1 minus, and then over here we have, should have erased that, x times x minus 1 primed here, folks. So this is minus x, because x minus 1 primed is 1. All divided by x minus 1 squared. And that's, x minus x is going to cancel out, and we're going to end up with negative 1 divided by x minus 1 squared. Now, what do we see, folks? And this is really important here. I want to emphasize here, folks, this here, without any sort of complicated discussion about signs and such, this here is always going to be a negative number. Why is that? I have negative 1 at the top. I have a square, perfect square at the bottom. This perfect square is always going to be a positive number. Negative 1, always negative. The quotient is less than 0. All right. So this number 3, less than 0, we got the sign of a derivative. What does that tell me? It tells me that the function, folks, is always decreasing, so y is always decreasing. All right, now the problem is that because a function is defined on two different intervals, uh, this decreasing situation is going to go down, but it's going to go down in different ways. We'll see when we graph a function on the two intervals that it's defined there. All right, so that's y prime. Now let's figure out the y prime prime part. So remember that y prime is -1 divided by x minus 1 squared. And now to review it for everybody, because we'll have this on the test, it's going to come up on the test. So we're going to do the chain rule again. I'm going to test it. So this is the same as negative x minus 1 to the -2. And when you do the derivative, the second derivative, this is going to be -1 times -2 times x minus 1 to the -3. Okay, so again, folks, what happens here, so when you do the derivative, make sure, you know, it's u to the -2, subtract 1 would be -3 times, and I would have times negative x minus 1 prime. That's the chain rule. But then x minus 1 prime is just 1, so I can wipe it out and I can say, well, this is 2 times x minus 1 to the -3. All right, folks. So this thing is the result of the second derivative. And now for the second derivative, we have to be careful because this is not always positive or negative. In fact, it's changing signs. And to study the sign behavior, let's point out there's one here. This number is never going to be 0. So because it's the same as 2 over x minus 1 cubed, and it's never 0. The top is never 0. So with zeros, we're done actually, but the function is undefined here, and if negative infinity is here and positive infinity is here, y prime prime has the following sign. So pick yourself any number you want less than 1, let's say 0, and you plug in that number, and you'll see 2 over -0 minus 1 is -1 cubed. So that's going to be a negative number. So this is going to be the derivative. The second derivative is going to be negative here on the interval negative infinity to 1. And over here, so let me shade that part to understand, everybody understand that there's nothing under 1. And then it's going to be positive on this other side from 1 to infinity. So when x is greater than 1, look, folks, let's say x equals 2 or 3 or 4 or so, this number 4 minus 1, for instance, is positive, and cubed is positive, so we're all positive. So this is going to be negative and positive like that, distributed like that. Now, the entire behavior of my function, folks, depends on how I use these facts. So again, y prime prime is here. For y prime, we already figured out is always negative, less than 0, right? Y prime prime has this sign. What is the behavior of my function? Well, the behavior of my function I'm going to describe underneath, under this exact same thing, same graph here. So the behavior of my function will be, decreasing and concave down. Something, oops, sorry about that. I made it almost nice, and then at the end I messed up. So decreasing and concave down. Why is it decreasing? Because y prime is less than 0. Negative y prime prime tells me concave down. And then my function is going to be also decreasing, but concave up. So it's going to go down, but it's going to go something like that. So I'm almost done here, and somehow messed up that part. There we go. So this is the kind of sketch that I expect to have for my graph. Now let's put the graph together and let's finish our lesson here. So I told you that these problems take a little bit of time, folks. So I'm going to do the graph. I'm going to draw the line, vertical line here, and the horizontal line over here. And I'm going to draw, that's the x-axis, that's the y-axis. Oops. A red line here to, come on, trying to make a selection here. So at x equals 1, I have this vertical asymptote. You know what? Let's do that again. X equals 1. There we go. That's my wonderful vertical asymptote. So let's say this is straight. I'm just going to assume it's straight. It's not very straight there. This is 1 here, folks. All right, and with blue color, I'm going to sketch my graph. So by the way, what is the horizontal asymptote? Oh, I forgot to draw that. So the horizontal asymptote also with blue was it, and let's see, what was that? So x equals 1, I know the vertical asymptote, I said there, yep, the vertical asymptote, x equals 1 over here on this page, and y equals 1, horizontal, okay, so it's also a value of 1, but it's in a different way, so let's say a value of 1 is here, then I'm going to draw a vertical line, a horizontal line, that's a horizontal asymptote this time around, right? Something like that. Okay. So I move that and I put it right there. So this is the number 1 as well. So these are the vertical and horizontal asymptotes of my graph. And now my graph, which again I am going to draw with blue, has got to be, and I look back here, and it's got to be before 1 has got to be decreasing and concave down. So let's judge ourselves. So it is decreasing, concave down, and towards negative infinity is tangent to this one. So how could it be? Well, the only way that could be would be something like this, folks. So this is the only way you can make it decreasing, concave down, and also closer to these asymptotes over here. So that's the only way. And the other way around, so for 1 to infinity, decreasing and concave up, there we go. So that is the graph that I am looking at. And this is an approximation. Again, if you want to stabilize a graph, you want to find out where it intersects the x-axis, for example, you can look at the initial expression, which was x over x minus 1. And it turns out when x is 0, it goes through 0. So I could have been more precise and I could have said, you know what, it goes through this point through 0, 0 here. But I don't need to because, you know, the way the graph is just sketched, you know, it's sufficient to have a good approximation of the shape. All right, folks, so that is the thing that I wanted to do here in this lesson. So this is probably the only graph that I'm going to sketch by hand. If you want to check that this is the case in Desmos, we can do that quickly in Desmos. So let's do that quickly in Desmos here. F of x equals x over x minus 1. There we go. That's a green graph. I'm going to say the vertical asymptote is x equals 1. That's the purple there. And the horizontal asymptote is y equals 1, which would be the black there. And you can see that that indeed is the graph as described in our picture. So that finishes up our discussion here today.